Okay. Welcome back. Fabian and we have the pleasure to introduce David Beazley to you. Why do we have David here? Well, Fabian and I were sitting virtually together in a keynote by Dave at the EuroPython 2021, and we were just impressed. We were constantly reminded by our previous research work in mathematics, I especially of category theory, and after the talk, we just sat down and said, well, Dave, you would be a great speaker at our big tech day here. So we invited him, and we are pleased that this year finally he is here. So,
okay, thank you.
Yeah, but of course by now we have done our homework, so by now we actually know who Dave is. So let me give you a short introduction. So David Beazley is an independent computer scientist living in Evanston, Illinois. He gives advanced programming courses, but probably he's best known for his great achievements to the Python community with books such as the Python Cookbook or Python Distilled. He created, in the old days of Python, the Swig tool to create C, C++ extensions, and he was the first person to port Python to a massively parallel supercomputer, the CM5. Also, Dave was an assistant professor of computer science at the University of Chicago. And well, apparently, lately, he's been starting to teach himself how to program. And so he will tell us, and I have to quote here, whether an old programmer still can learn new tricks. Just quickly, an organizational note. Of course, we will have room for questions after the talk. If you've been joining us remotely, please just put them into Slack before the question part. And now, with no further hesitation, it's very nice to have him here. Please give a very, very warm welcome to David Beazley.
All right. Okay. Yeah, thank you very much. First time in Germany. I'm very excited. So one of the things about giving a talk is when they ask you to give a talk and they ask for a topic, you just put whatever's out in your mind at the time. And so at the time that they asked me about this talk, I said, oh, I was going to talk about this. And then preparing the talk, I was like, there's no way I can talk about that. So in order, the solution to a problem like that is to talk about the complete opposite of that. So I'm going to start by talking instead about the 25 attempts that I've had at implementing the raft distributed consensus algorithm. Actually, I'm a little curious, has anybody come across raft before or heard of it or anything? It's really kind of a cool problem. So let me kind of introduce the problem and why it's kind of neat. So basically what raft is about it's about kind of fault-tolerant computing and like how do you make like a fault-tolerant service of some kind. And maybe just as an analogy of that, maybe some of you have seen this cartoon about the dependencies, where you've got the one piece that's holding the whole stack together. Raft is kind of about that, but for the network. So imagine that you've got a whole bunch of machines on the network. These are all sending messages to each other. And one of the things that you might find on the network is that one of these machines appears to be more critical than the others. Like maybe it has a lot of arrows kind of coming into it. And then you start asking questions about, well, what happens if that machine dies? What happens to your network? And what can happen is that you can end up like getting like 50 million kids basically mad at you. Like an example of something like this. I don't know whether you have any kids that play Roblox or something like that, but like 2 years ago, Roblox went offline for 73 hours. 50 million players, daily players. And you're gonna ask me, why would it go offline like that? Well, one of the ways it would go offline is if some critical service died, and then it had like creeping death or something. So one of the solutions to that is to replicate it. It's like, okay, well, let's put more, like instead of having one critical service, we'll just replicate it 3 times. And then the idea is that if one of them dies, you have like 2 others, right? You can keep on running with it. So raft is basically about that. And what I'm gonna do is just talk a little bit about kind of the high-level view of what the problem is about, as opposed to the algorithm. So I'm not really gonna present the raft algorithm, but I'm just gonna kind of step you through it. And then I'll talk about why I'm talking about this in a second. So essentially, this is the high-level view. You basically start with a traditional network program, like a client-server app. think the web, your standard kind of thing. What you're going to do with raft is you're going to replicate the back end of that. So you're going to have like 3, instead of 1 server, you're going to have 3, but the 3 are basically going to look like a collective whole. Like from the point of view of the client, they're only talking to 1 server, basically. It's just like there's this 1 service, but there's like these 2 backup servers kind of running in the background. And the whole thing that you're thinking about here is that you want to have this thing survive under the failure of one of the machines. So if one of the machines goes down, you're going to have 2 others that can basically step up and kind of operate, or can continue to operate. Now, the problem with doing this is how do you make that 3-node cluster operate as a consistent whole? And it turns out to be a rather kind of tricky problem to do that. So here's kind of the coding concept on it. You basically start with like a traditional network app, your client-server app. What usually happens with this is a client would send a command to the server, set X to be 2. Think of it as a database or something like that. The server would then execute the command, and then it would send a reply back saying, okay, that's fine. What you're going to do with that is you're going to extend it slightly. By the way, this is just standard networking stuff. It's actually what I would call kind of like a homework problem for networks class. So if you've ever taken networks, you probably implemented something like that. So what you're going to do is start with that, and you're going to extend it slightly by adding a write-ahead log to the application. And the idea with the log is that basically a client will do a request. Okay, they'll say, set X2. And then what you're going to do is you're going to write the request to the log, which is going to be on persistent storage somewhere. It'll be like a disk or something like that. And then once it's written to the log, you'll then execute the request and then send a reply back to the client. One of the things that's going on here is you're thinking about crash recovery. So if the server crashes, how do you get it to come back? And one of the ways that you would restart it is you'd restart the server, and then you replay that log, and you get back to where you were. So this is kind of standard stuff that you see in databases and other things. I would claim that this is maybe an additional homework problem, except for the extra 2 months figuring out how to do persistent storage correctly. Okay, so I don't want to talk about that, but if you know anything about persistent storage, it's kind of a horrible problem all by itself. So you have that, and then what you're doing with this raft thing is you're basically adding a replication mechanism to it. So what's going to happen here is a client's going to send a request. Okay, request comes in. You're going to write it to the log, but then what you're going to do is you're going to copy the log to the other machines. Okay, so there's going to be kind of an outgoing message that gets sent to all of these kind of follower machines. And then they're going to write the request to their logs, and then they're going to reply back to the leader, basically saying, I was successful in writing to the log. And then the leader is going to watch this, and as long as like a majority of machines reply, and this is kind of tricky. Majority just means like if you have like 3 out of 5 machines or 2 out of 3 or something like that. It's just a quorum. So if you can get like a response from 3 out of the 5 machines, then you tell the client to go ahead and, well, then you execute the command, you need to tell the client about it. It's a little bit more complicated because there's some follow-up to that. Basically, after you've told the client that you did the command, you have to tell the followers to go ahead and do the command as well. And then they execute the request. So one of the things that's kind of happening here is you've got this leader machine, and then it's basically trying to keep these follower machines in sync with itself, as it's doing this. So that's part of the problem that's going on there. The other thing that's going on with raft is there's this notion of leadership and timeouts. Okay, so to make the thing work, one of the things that you're thinking about is how is this thing going to fail? Like what happens if it crashes? And so basically every single part of this system has some kind of timeout attached to it that is waiting for something to happen. And so if one of the machines dies, so let's say the leader goes away. Okay, so leader crashes on it. What will happen is these other services or these other machines will eventually time out, and then they will try to correct the problem that has happened here. Okay, so what will happen in this case is one of the followers will step up to become a leader. So one of the other machines will basically take the place of the dead leader. Since it was tracking the leader the whole time, it should have all the information from like the application. Okay, so it's been following this leader the whole time. What will happen on the client side is it will time out and then maybe do a retry with one of the other machines. Like it will say, I don't know what happened to that leader, but I'll try to do my command again on one of the followers or something. So this is kind of the gist of it. I've left out a huge number of details here. Okay, I mean, in fact, that is not the raft algorithm at all. What I've presented there, that is just basically a high-level view of what the problem is. But one of the things about raft is there's this paper that describes it, and they claim that this is sort of an understandable algorithm. And I would agree that the concept at least seems kind of understandable. It's like if you want to have fault tolerance, you're going to have this machine replicating itself, and you're going to try to keep the state in sync. And it seems like something that you could implement. So I don't know whether you agree, whether that seems like something that could be implemented or not. I don't know. I mean, do people just seeing that description, does that seem like something that could be coded, or? I don't know. Okay, some nodding there. Okay, so I got interested. Let me talk about why I'm talking about this and why I'm kind of interested in it. So a little bit of backstory on me. I've done a fair amount with massively parallel computing and systems programming. As it's mentioned in the intro, used to teach operating systems, done a lot with sort of Python concurrency. You can kind of blame me for blowing up the global interpreter lock in Python about 10 years ago if you followed that whole thing. So I have kind of a general interest in this topic, and I had actually never encountered raft before until 2018 when I was learning about a different topic. I'd encountered this tool, TLA+. Actually, have people encountered TLA+ in here? This is basically it's like formal verification. What? Yeah, Leslie Lamport. I'm plugging Hillel's book because he's the guy I took the class from, and he's also in Chicago, so he's a nice guy. So I took his class, encountered raft in there. The course wasn't really about raft, but I saw raft, and I started looking at the paper, and I'm like, wow, this is a really interesting paper. This is cool. This is like, it's got networks and messages and distributed computing stuff. I was like, oh, this is great. And then, so I decided, in 2008, I would give part of it as an assignment to a class. I would just like, hey, why don't you implement part of this paper? And I have to apologize to those students for that. One of the things as an instructor is usually it's a good idea to try something before you assign it. I just should have tried it. Okay, so tried that. So that ended badly. And then over the holidays, I was like, well, I'll code this using Python and 0MQ. And 0MQ is this really nice messaging library. And I went into it thinking, wow, how bad could this be? Understandable algorithm and all this stuff. And it was just terrible. I mean, it went down, and like I figured it was too soon to show the submersible, so I didn't show that. But no, it did not end. It did not end well for me. So the obvious answer to that was actually to turn it into a course. Like, if I can't do it, I mean, we might as well just teach it, So I set up kind of I do these week-long courses. So I set up this course where it's like, come in and implement raft, okay? And the goal was to do it in a week. It's like, take a group, let's do this for a week. Raft is actually a pretty common course project at university. Like if you see a distributed systems class, they might implement raft over maybe 5 or 6 weeks or something like that. Keep in mind, like university students have other things going on. So figured we could do it in a week. I would say mostly this has been failed to implement raft in the week-long thing. I'm going to talk about that a little bit, but part of the reason why I was doing this is I'm actually really interested in just kind of programming as like a problem-solving exercise. It's like, how do you break a problem apart? How do you design it? How do you test it? How do you think about it? How do you debug it? I mean, there's all this stuff that you do in software, and I think like most people, would like to do things kind of the right way, right? You know, it's like, oh, I want to do things right. I'm going to do clean code. I'm going to do test-driven development. I'm going to do all this stuff. And so here's this kind of, you know, this small, understandable project where you can apply all of this stuff, and you hope to not do the thing on the right. Okay, so that was kind of the goal on it, and on top of that, the problem actually is kind of well separated. I mean, there's kind of a, there's an application, and there's networking, and there's this replication thing, and elections, and so there's these parts, and you kind of get into this project, and then it starts to go horribly wrong, sort of no matter like where you started. So I wanted to talk about that a little bit. So one of the approaches on the project, actually this slogan is from Google, by the way. I don't know whether there's any ex-Google people, but when you used to go to Google, they'd have all these signs pasted around the building, you know, debugging sucks, testing rocks. Okay, so one of the approaches that you might take on this is I'm going to focus on testing, you know, test-driven development, that sort of thing. Turns out it's really kind of punishing in this project because there's like this giant like state space to the problem, and there's a lot of really tricky edge cases. And just to give a sense of that, first of all, you're working in this kind of fully interconnected cluster of some kind. And then you have to account for the fact that there's multiple clients connected to it. So you have like multiple clients interacting with this cluster. You have to deal with dead machines, because that's part of the whole algorithm, is dealing with dead machines. And then there's other things that can happen, like dropped messages. You can have duplicated messages. You can end up with like network partitions, like what happens if half of the cluster can't see the other half, and then like, do you have like a dead leader that's just sitting up there, doesn't know that it got cut off, and then do you have like new leaders? And so you can have all these things like split networks. You can potentially have like simultaneous elections going on. This is only one will win, but you can actually have like machines trying to fight over elections and all this stuff. And you get into this question of like, well, how do I test for all that? I mean, like any one of these things, it's like, I'm going to write I'm going to write a unit test for that. Like what is that? Okay, so this you very quickly end up with what I would describe as kind of like the 9 circles of dependency injection hell or something, doing that, or mocking hell, if you know about that. So that usually ends badly. Another approach on the project, you could basically abandon testing and just say, I'm going to focus on debugging. I'm not going to actually don't take that advice. I actually taught the course that way once, the raft course, because the testing was so hard. I decided I was going to go all in on debugging rocks, testing sucks. It ended horribly, by the way, so don't do this. But the debugging part of this is really bad too. It's kind of like I would describe it as kind of everywhere, you know, all at once debugging, where you've got like sockets, you've got threads, you have timers. Does anybody have code like timer stuff? You deadlock, you know, kind of conditions. Knowing the latency numbers, like this is from one of these famous things, like latency numbers. Every programmer should know. That actually becomes like super critical with something like raft, because it's almost the opposite of everything you do with like a lot of distributed computing. Like if you want fault tolerance, you don't put all of your machines in a single rack. Like that would be dumb, right? It's like, it's good. What if it burns down or something like that? So the machines are often like physically distant, and you're dealing with like speed of light and latency numbers and all this stuff, and it actually has a big impact on like the debugging and the timing of it and all sorts of other stuff. So it gets really complicated, and then you often find yourself building dashboards all the time, or it's like complicated dashboards of what's happening, what's going on, and then if it does break, God help you if you need to figure out why it broke, right? Okay, but you have the dashboard on that. So you could do a third approach. I mean, this is another approach. You could do the testing sucks, debugging sucks approach. This is more of the I'll just try to code it right approach and see how it works. This is from the 0MQ document. One of my favorite quotes in there is just talking about multi-threaded programs turning into drunken bar fights, and then it's like you could look at that and say, well, I got to try to avoid that. Maybe I'll code the whole thing using actor model or something like that, and then you realize it's still terrible and complicated, and then somebody will suggest to you online, it's like, I don't know, have you tried using async or something like that? This is like a totally irrelevant question to the whole thing. So the end game of this raft thing, usually at the end of the week, you just end up with this kind of raft-like thing that's sort of broken in every way, like broken testing, broken debugging. All the abstractions are wrong, and it's kind of just patched together in some way. And then people can ask questions about that. It's like, well, why don't you look at some existing implementation? And it's like, okay, fair enough. Or use some specific programming language, or some framework, or a design pattern, or plug it into AI and see what it comes up with. But doing that I think kind of misses the point of the exercise. I mean, it's like why would you implement raft 25 times or whatever? I think one of the challenges on something like this is kind of this. Well, there's like the famous Feynman quote. I mean, there's like this idea. What it can create, I do not understand. So part of the challenge here is you've got this really tricky problem, and how do I do this? It's like it's like a personal pride thing, right? Where it's like, I should be able to code this. And it's like, why can't I code this? The other thing that's kind of interesting. This is something from Peter Norvig. I don't know if people have seen this, like how to teach yourself programming in 10 years. And one of the things in there is he talks about deliberative practice. One of the things to get better at something is to just do it over and over again, and then kind of analyze what you're doing and why did it fail, how you can make it better, and so forth. And I sort of feel like inadvertently I've kind of fallen into that with this raft project, where it's like I'm coding it over and over again and seeing different things and failing repeatedly, but in different ways. So that's sort of interesting in that. One thing that I've kind of concluded on the whole exercise is that I'm not sure I actually know how to program. I think we're getting back to the talk title in here, right? Something like, do I actually know how to program or something like that? So I'm going to shift gears slightly on this. So by showing, talking about my deer accident. The deer is okay, by the way. That leg, that's fine. So right before the pandemic, I hit a deer in the face while cycling and broke both my hands, doing that. It actually happened on Friday the 13th, believe it or not. So kind of amazing. And then you get asked, what was I teaching at the time? I was actually teaching lambda calculus the day before, and I was like, why is he doing that? And I'm actually going to blame lambda calculus on the wreck, because I was probably not thinking about deer or where I was going at the time. But this whole accident is kind of related to what I really want to talk about in this talk, is some things that happened afterwards. So one of the things in my background is I kind of have this timeline of doing things with concurrency, basically parallel computing and teaching operating systems and networks and raft and TLA and all this stuff. But there's this other timeline where I've done some stuff with compilers. Like I took compilers class. I wrote this Swig tool that does Python C++ integration in the 90s. I've done some stuff with parsing tools, and have kind of continued doing some stuff with just compilers, programming languages. I got interested somewhat recently in the famous SICP book. This is a fairly kind of theoretical book that's was used at universities. I taught that, and then at the PyCon conference in 2019, I sprung lambda calculus on them as a tutorial. It seems kind of an unlikely topic for a PyCon conference, but this is kind of like if you write a Python book, you can often spring something like that on people before they know what it is, before the conference committee realizes what you're doing and realizes it has nothing to do with Python. But so I was doing that, but basically the crash kind of happened there. And then there was kind of this whole kind of question, what am I going to do with my time with the 2 broken wrists and the crash and all that stuff. And for reasons I don't really know, I decided I would go watch lectures on category theory. Now, I have like no reason to do this. It's like I'm not programming Haskell or anything like that. It's just like, okay, let's go do category theory for a while. And then the pandemic hit about 4 months later. I was actually watching the category theory videos in the gym, believe it or not, like on a Stairmaster or something, like doing the stairs, and then watching category. There weren't too many people nearby, actually. They kind of kept their distance. So pandemic hit. Once that hit, things got a little weird, got a little strange. I ended up doing the raft course about 20 times, kind of over the next 3 years. But one of the things that was kind of surprising is that category theory thing really kind of got on the brain a little bit. And I actually found that the two topics that have helped the most in the raft project have been the lambda calculus and category theory. And it seems really weird that would be the case. Like why would those things have anything to do with this raft project? I mean, they're almost like the total opposite of that. I mean, like if you know anything about either of those topics, like what on earth could they possibly have to do with raft? On top of that, it's like I'm like coding in Python. It's like why would you do that? So I wanted to say a little bit about that. Like, why would that be the case? So if you go look at lambda calculus, it's this really theoretical, highly abstract thing. How many people have been exposed to that? I'm just a little curious. A few hands. Okay. If your exposure was like mine, I couldn't see any point to it at all, other than it being kind of a curiosity. When I first learned it, I was like, "What is this thing?" And like, it took a while to kind of internalize it. So I wanted to kind of back up to something a little bit more basic. This is actually something that kind of helped me internalize lambda calculus. So when learning computers, kids are often taught about ones and zeros. It's just like, oh, it's ones and zeros, it's bits. And you can kind of go from bits to things like wires and switches and stuff. And you can say, oh, 1 and a 0. It's like a switch. And you're talking about the output of the switch. And, if it's 5 volts or 0 volts or something like that, it's like you have on, off. And one of those can be 1 and 0. And maybe that one, maybe it's true or false or something like that. The choice is totally arbitrary, by the way. I mean, it's like you could make the 5 volts 0, and the other. Basically, like one of them has to be 0, and one of them has to be 1. True and false. So you might start with that. And where something like lambda calculus comes into it is this idea of, actually, before we get to that, you can build things with switches too, like and or and circuits and all this stuff. So where something like lambda calculus comes in is this idea of abstracting away things. Like you could ask a question like, what if you just got rid of values? This is kind of a weird thing in programming, actually. Like if you were just to go to somebody like a Python programmer and say, what if you just got rid of all the built-in data types? Like just get rid of integers and like everything and just, I don't know, try to do something with it. Could you still make sense out of what's going on? And it turns out that you can. Like on a switch, you could focus on the switch part, basically, and you could model that. You could say, well, this switch has 2 features. It's left or right. You have like 2 inputs. And you could just say, well, the left returns A and the right returns B. Now, I don't actually care what the A and the B are. But this is not modeling the output. This is just modeling a behavior of the switch, where it's just like, well, it's left, you get A, and if it's right, you get B. You could call left and right true or false if you wanted to. Maybe true just means that you're on the left and false means that you're on the right. It's totally arbitrary. It could be the other way around. Maybe false is on the left and true is on the right. The important thing is that those things are in opposition to each other. It's like one is true and one is false. And the thing that kind of blew my mind is in that kind of formulation. Here's what it looks like in lambda calculus, by the way. You can still do things. Like you can define logical operators, and you can do like math kind of things entirely in this really weird world of abstraction. And it looks really weird and impractical and so forth. But one of the things in this, it just makes here, it's kind of like if you get into this, it's like a really big mind warp. Basically, it's like you end up with functions and no values. And actually, to make any sense out of it, you almost have to dimensionally shift your brain into like a different mode of thinking. That's actually kind of where the title of this talk comes from, by the way, is trying to shift your brain. But here's where this kind of comes back to raft. In this project, you are basically dealing with a lot of like boundaries between software components. And there's kind of this world of the abstract and this world of the concrete in a sense. And that is something that happens a lot in the coding of this thing. What I've kind of drawn here is like a boundary. And there's all sorts of things that you can think about on opposite sides of a boundary. You can think about, are you talking about behavior or values? Are you talking about sequential code versus concurrent code? Are you talking about logical networks versus actual networks, or logical time versus actual time? Like what kind of universe are you actually working with in the coding of this? And you can ask, well, who cares? It's like, who cares about that? It turns out that the choice might have a huge impact on something like testing, for instance. Like, you're going to code this raft thing up. What universe are you writing the tests in? Or where are you operating in the problem space? And you might realize that on one side of that boundary, you're in like just horror zone, where it's like, this is seriously bad. Whereas on the other side of a boundary, you're in like a happy place, and so forth. And this is this idea of boundaries and being able to abstract stuff out is something that is like really common in kind of the distributed computing world. This is from the Joe Armstrong dissertation on Erlang. So Erlang is a programming language used for a lot of distributed computing. And one of the things that's in there is he talks about abstracting away details. Abstracting out concurrency. In some sense, lambda calculus is maybe the most extreme that you can get with abstracting away stuff. It's just like, we're going to get rid of everything. And then you're going to try to work with nothing. And it's like this really like mentally punishing kind of exercise to do that. But it's sort of weirdly useful in trying to think about this raft project from first principles, where it's like, I'm looking at this complicated problem. How do I abstract away stuff? So there's that. The other topic that I mentioned was this category theory topic, which is maybe even more abstract in a way. I'm not actually prepared to really talk about category theory, because then I would have to admit that I understand it, which I don't. So, like the 100 hours of category theory lecture that I watch is not enough to understand it at a level to explain it yet. But category theory is also this highly abstract thing, and I thought I would give kind of an intuition of some of the thinking on that, at least as it relates to me. So earlier I had this slide with objects on it. You might have objects, and then you might have arrows kind of relating to objects. One of the things that happens in this category theory is this question of, what if you just got rid of all the objects? It's kind of like the analogous thing with lambda calculus. Like, what if you just got rid of all the values? Well, if you got rid of all the objects, you would just end up with arrows. And in some sense, that's what category theory is about. It's like, what if you only could look at the arrows? Could you make any sense out of what you see there? This is the kind of thing you see in category theory. There's lots and lots of arrows where they're talking mainly about like function composition is the big thing there, but it's lots of arrows. And you get into this kind of weird mental thinking about like things like this, like, what's that? I don't know, what is that? Any thoughts on that? Well, you might look at something like that and say, well, that's clearly a pair, a pair of values. It's two values. And what the arrows actually represent is your ability to split it apart. Like, if you had like two values, you can get the left value and the right value. And so that's some of the stuff that you run into. You might run into more advanced things. This is actually the thing that I had on the opening slide, which I was hoping to talk about. This is the Yoneda lemma from category theory, again, which I'm not prepared to talk about in great detail here, but this is something that has been, it's kind of fried my brain a little bit in the thinking of what is going on here, and I thought I would try to explain maybe what's going on with this. So here's kind of a weird question. Okay, so let's say aliens dropped some new technology on planet Earth here, and you were not able to deconstruct it in any way, like not be able to look inside or see anything about it. And there's this question of like, how would you understand that? Like if you had this mysterious object of maybe like perfect encapsulation, how would you make any sense out of it? And so one thing that you might do is you could just poke at it and just see how it responds, basically. It's like, I don't know, okay, well, I don't know, hit it with a hammer and see what happens with it, or blow on it, or something like that. The Oneida lemma, what that's kind of, what kind of the idea there is, if you want to understand it, maybe you could just watch how it interacts with every object in the universe. It's kind of broad, right? Okay, you could just poke at it with every single other thing in the universe and just see how it reacts, and then kind of watching it scientifically, you could understand it. And so one way of phrasing that, this is something that I saw in the 100 hours of the category theory, was this idea that you could understand an object by understanding how all the other objects interacted with it. And it kind of blew my mind a little bit. It's like, well, that's a really weird way of like thinking. And I thought about that statement, and I was like, well, what if you just took mathematical out of it? Mathematics, makes people run away and they get scared and so forth. So I was thinking, it's like, well, what if you just changed it? Okay, an object is understood by how all other objects interact with it. And then I looked at that, and it's like, well, that sounds too much like object-oriented programming or something like that. So maybe you could just like change it. Like what if you just change it to code? Like that sounds like really, like really generic. It's like code is understood by how all other code interacts with it. And could I make something like that maybe a mantra of coding the raft project? This might sound like kind of a weird thing to do, but I'm like in this project, and I'm finding it extremely punishing. Like nothing works in this project, and why? And it's like, could I take like a statement like that and apply it in some way? So this is where it kind of comes up. It's like you can think about, what is the nature of this abstraction barrier, right? It's like earlier I talked about how you could separate things out. It's like you have logical time versus actual time. But what is that barrier? Like, how do you cross that? And essentially, when you do the cross, you're talking about arrows. And when you're talking about arrows, that's kind of the domain of this category theory thinking. So some of the things that you might think about with that boundary are things like is it synchronous or asynchronous? Do you wait for results? Does it happen later? Is it like a really wide interaction across there? Is it narrow? This kind of takes you actually into the domain of things like design pattern and maybe like software design things, like API design. Like what is the nature of this API? Does it have like 100 functions in it? Does it have 2 functions in it? Like how deep are they? How complicated are they? And so forth. You're basically talking about arrows, like in API. So you're thinking about that. You might think about error handling. This is kind of a weird slide, but I'm thinking about, here's what I'm thinking about here is like you send like something across a boundary, and then you're getting some value back, but there's a possibility of an error. And like, how do you deal with that? It's like, is that like 2 arrows coming out? Or is it like some kind of other weird thing that's coming out? Maybe that's like a monad or something in disguise over on the right. But you think about things like this, and then you can, I thought about some paper I came across years ago talking about failure in distributed systems. Okay, so I think this was 2014. Actually, this is the same year that raft was published, 2014. So we wrote a paper studying failures in distributed systems, and one of the outcomes in the paper, you can see it here, 92% of all failures that we looked at were incorrect error handling. It's like, it's kind of interesting. It's like maybe error handling is something that I should focus on. So other things about that boundary, there might be kind of dynamic features of that, especially if you get into some of this distributed stuff with like things like queuing. You know, is there a queue across a boundary? And if there's a queue, do you end up with issues of things like back pressure and flow control and all sorts of other things? And, you know, does the positioning of that queue actually matter? You know, depending on where you put it, you might have things like implicit behavior versus explicit behavior. And like, does that affect how you debug it and how you design it and other things? Just as a note, I did have that slide about Roblox and the 73 hours going offline. That's what happens when raft fails, by the way. So that their failure was basically an issue with the raft algorithm itself. And it was actually, this is a really fascinating thing to read, by the way, but it's a lot of the failure had to do with a lot of dynamic properties of things like queue back pressure and other things. Some part of their system changed its behavior, and then it like took the whole thing offline. And it's like so those are the kinds of things you think about with think about with that. So, kind of bringing this back to the raft side. One of the things I've been really interested in with this project is just like, why does it go so wrong? I get a lot of people who have taken the raft course, so they're like super experienced programmers. You know, like 30-year programmers come in there. It's like, I'm going to go code raft with Dave. And they get to the end of the week, and they're like, Dave, that's the worst thing. That's the worst code I've ever written my whole life. And like, I hate you, and all this other stuff. So I'm really super fascinated. Like, where does this go? Where does this go wrong? And what I often see in the project is a lot of the failures are basically related to like interaction between pieces. It's like how do the parts fit together? And it can either be like an overly complicated interaction, or you can end up with like mixing abstractions, like maybe the boundary between like the different parts of the problem are not well defined, or they're kind of fuzzy, basically. And what ends up happening a lot is you try to fix all these problems with like quick hacks, and then the hacks like multiply exponentially, and then you end up with this like huge tower of hacks until you can't manage it in your brain anymore, and that just sort of blows up. So I've definitely been interested in just how do you get your head inside of this problem to make any sense out of it. And I think the thing that I've kind of found fascinating with this, you know, mentioning some of the other topics like lambda calculus and category theory is I'm interested, you know, I'm kind of wondering, like, do like formal systems like that, is there anything there to inform kind of like an actual system? Because I've found that like studying those topics has actually had a big impact on how I code raft. Like I've seen like improvements in my attempts at doing the project, but it's a little strange. I can't point to any specific thing from either of those topics where it's like, oh, I'm applying this like lemma out of category. No, it's like it's nothing like that. It's more like, I don't know, maybe just having the head in like a space where you're thinking about interactions and boundaries and other stuff. So I'm kind of interested in that. I have described it as kind of a dimensional shift. I mean, this is what I want to, you know, the very vague talk title for here. I was sort of thinking about, like, as a programmer, can I put my brain in sort of a different like dimension of thinking about a problem? Because this raft thing has proven so challenging. Like more challenging than like a normal problem, and it was just like how do I come to terms with that, basically? So that's kind of an interesting thought. The only other thought I have on the project is that maybe it just needs 2 weeks. I mean, it could be that. So that's the end of the talk. I'd love to have questions about that. Admittedly, it's kind of a weird topic, but let me see if there's questions or thoughts about any of that. So.
All right.
Did I come in under time? Am I?
Oh, we are perfect, I think. We have time for questions. Okay. So first of all, thank you, Dave, for this talk. Okay. I was definitely amazed. Questions. I think we start right ahead. Tillman, please.
Awesome. Thank you for the entertaining talk. To me, this sounds very much like a non-duality, what you discovered. I'm not sure if you've looked at all at this concept in a Buddhist context, actually.
A Buddhist? Well, no,
Yeah.
maybe. No, I haven't.
It's extensively discussed in, for thousands of years in I guess, Tibetan Buddhist literature and other Buddhist contexts. This idea that a concept is only ever defined in relation to its opposite, more or less.
Okay.
Like self, other, boundary, and so on. Maybe you should look.
I mean, that's a big idea in the category theory stuff. As they have this concept of reversing all the arrows. It's like, okay, you have all this relationship, and it's like, actually, what if you just reverse everything, and then what happens? And it's like, huh. I actually have found that useful in the raft project too, where it's like, oh, this is totally bad what I'm doing here. What if I just did the total opposite of that? It's like sometimes works out like that. Actually, this is sort of maybe somewhat tangential. One of the things that kept me going on the category, if you're going to look at category, I find it punishingly abstract. Like, I wouldn't say that I understood most of the 80 hours. I mean, it's like it got like little glimpses of it. I think the thing that kept me going through that is it seems like everybody who talks about category theory has this like crazy look in their eye, like where they're like, this is the coolest topic in the whole universe, and I can't tell you why, I can't explain why, but they have this like excited, good sort of crazy look on it. I'm like, there's part of me, it's like, I got to keep going because I got to know where that look is, like where is that coming from, or why, I just don't. Maybe I haven't spent enough time on it yet, but it is sort of wild. So.
Questions, please raise your hands. I think you had one here, then continue first.
Thank you so much, David. Like this.
Okay.
Thank you so much. What a fantastic talk. I may have zoned out or dimensionally shifted at some point, but I didn't really understand how the lambda calculus and category theory helped you solve the raft problem. And maybe it's too much detail to go into now, but can you give me concrete? Or alternatively, how do you work with category theory and make money doing it?
Yeah.
But in order to solve problems.
So I don't understand either. I don't understand like why are those impacting raft? I mean, maybe an analogy might be like weightlifting or something like that, where it's like, okay, you go out, you do weightlifting, and it's like, okay, in my day-to-day job, I'm not paid to do weightlifting. Okay, at least most of us anyway. And maybe it's that kind of thing, just with like a mental exercise. It's like you're in this really abstract space, and I find it like really challenging to just get like your brain wrapped around this really challenging kind of system. But in those, like in things like lambda calculus and category theory, they spend a lot of time thinking about how the whole thing kind of fits together. It's like, is there like a theoretical foundation, or it's like how is this whole system put together? And in some sense, that's the problem with raft. It's like, how is this system put together? And maybe there's some kind of crossover where it's like you see something like category theory, and you're like, oh, they've put it together like this, and then maybe you can get like a little glimpse of an idea where it's like, oh, maybe I could apply that in raft, or some similar kind of thinking around it. But I wish I knew, like, the answer to the question. So.
Thanks. Very illuminating, and I feel like being on a similar track. For this, how could it contribute to the raft problem? My first university degree was in electrical engineering, so we have the Fourier transform, and it's everything. I mean, it's much more to electrical engineering than the Fourier transform, but you have a different kind of perspective on everything that happens in time, and you know that there is somehow this different perspective which you don't have if you look at the world, but it's there and it's equivalent. And for me, it seems like with a category theory and so on, everything that connects to sequence and time, and that obviously is the main thing that makes the raft thing so complicated, race hazards and everything. It's basically only sequential things that can be combinatorial in explosion. And in category theory, nothing is sequential any longer. You have it all rolled out in static, holistic structure, but the concept of time evaporates, and you have the full information in a different kind of dimension or space. And that is maybe something that I feel could help there, because suddenly you get rid of all these sequences in the formulation of the problem.
Yeah, figuring out time is actually a really huge problem in the raft project. It's like, can you abstract away time? And maybe a good analogy for people who've done like a lot of coding would be like, what if you have to deal with time in testing? Has anybody dealt with that? Like if you've been writing unit tests and you've got to like, oh, I got to put like a sleep in here, like a time sleep, and then because there's some delay and there's some kind of a timing effect, and that kind of stuff tends to kill you on the raft project. And it's like, so if you can think about how to get outside of time into some kind of, like logical time or some other thing, it's really tricky. That's something that I see a lot in that project that just kind of blows people's minds, like how to wrestle with the time part of that. Yeah, do we have time?
Okay,
I see one
maybe
question.
one final question, right, Florian, over there? Because we've basically run out of time.
The talk is timeless. We could just go for...
Our schedule is still quite linear, unfortunately.
So thanks also from my part for this very inspiring talk. I have actually maybe a clarification question. Since we've been talking about raft so much, so it kind of feels to me, or at least I have a tendency, maybe to blame the raft specification a bit for not considering all the questions you've been bringing up. So with the benefit of your perspective, would you say like maybe the raft specification is just underspecified, or is it our way of thinking about the problem that's where the challenge lies?
I don't know whether I'd describe the spec is underspecified. I mean, it's the paper itself doesn't really say a whole lot about how to implement it. So I don't know that totally answers the question, but it's...
I mean, like, it seems like all of the problems you've been describing to us, the people who have written the specifications or the specifications should have thought about and maybe given some kind of direction to go in.
Okay. I mean, they did try to prove raft with TLA+, so it's like the algorithm has been formally verified, but then there's, I think part of what I'm wrestling is how do you go from like formal verification to actual implementation, which is like probably a whole nother talk actually, because it's like those two worlds are often very separated from each other, where it's like, okay, if you've proven something and now it's like, okay, go code it in Python, and then you're kind of in a world of pain doing that. So.
Thanks.
All right, I think we are out of time. Now that's a coffee break, but before that, of course, let's please thank our speaker again. Thank you so much. All right, very nice to have you here.